We're going to talk about Conway's game of life, which is a cellular automata concept that was described back in the 70s. It's pretty interesting. Many of you are probably familiar with it. If you're not, I encourage you to go and read about it a little bit. If you're a computer science person or a science person, you'll probably find it interesting if you haven't seen it before. The rules are pretty simple. You have sort of a 2D matrix. Values in the matrix can either be 1 or 0. We're going to use integers for this later because there's not a good bit value in MPI-2, but that's not that important. You initialize, and then at each iteration, you look at the surrounding cells, and if the sum is 3, or the value is already 1, and the sum is 2 or 3, then you get to stay alive. Otherwise, you're lonely, or you've got too many people around you, and you die. And that's the way the game is played. And it used to be this was animated. It still is animated. This was from when I put this animation together when I was younger and more pessimistic. And so my scenario is such that in about 2 more iterations, yeah, there you go. So I'm a brighter, more positive person now. But anyway, so that's how this plays out. And so what we're going to do is we're going to use this as an example for showing how we might build a library for managing storing of a matrix like this. And as you can imagine, storing a matrix like this is really not that different than storing other types of matrices, which sets you down a path to understanding how you might build a library for checkpoint restart. Okay, this is where there is this code available if you're interested in having a look at it. We're going to look at the code in slide form, so if you don't have the code up, that's fine, but it might be helpful to grab it. So for a non-parallel version, you'd allocate a 2D matrix. Really, you'd have 2 so that you could have somewhere to put the next state as you calculate it. You would initialize that matrix, generate some internal state, and then at each time step, you calculate the new cell states based on the algorithm that I just laid out. Store those in the next matrix, and then swap them and repeat, right? Pretty simple. In a parallel version of this, we're going to have that same sort of global notional array that I just described, that 2D matrix, but we need to describe to ourselves at least, and then in code, how that is decomposed across the processes that we're going to perform our computation. Then we need to think about how we're going to communicate data between those things, and then ultimately define the local arrays and the communication in code. So here's what we're going to do. We're going to take our 2D array and we're going to decompose it. Imagine we had 4 processes. Each process we're going to do a simple row block decomposition. Okay, there's lots of different decompositions. I think most people who have done parallel programming with dense matrices understand that row block is often not the best choice, but that's what we're going to do today because it's easy. So step 1 is we pick a decomposition. We've done that. Step 2, we're going to think about how we're going to do communication, right? So recall that we need this stencil, the neighboring cells, in order to calculate updated state for the next step. And so for these rows that are, I'm going to get myself with this, and I'll be in trouble. For these rows sort of in the middle, that's no problem, but if we're along an edge of our block of rows, then we might not have the data that we need. And so we're going to allocate some additional space on processes to store information from our neighbors, and then we're going to use send receive to get that data from our neighbors, or RMA to get that data from our neighbors. I'm not going to go into that communication step. You may have seen that in the other tutorial. If not, it is in the code examples. Okay. Now, just sort of a point that we'll get back to in a little bit. The green rows, these sort of duplicated rows, are redundant data. And in this example, there's not that much redundant data. And so if we were lazy, we could store that redundant data in our checkpoint. but because I'm trying to show you a good example and not a lazy example, we're going to skip all the redundant data in our checkpoint and in our restarts. Okay, so probably obvious, there's not going to be a single global array allocated anywhere. Instead, each of our processes will allocate space for their local arrays. We'll perform the computation in parallel. And our goal during our checkpoint and restart will be to interact with the storage system using the logical global array so that we don't have to think about how many processes we ran the original code on and things like that. And this will be clear in just a minute. Okay, so we've already talked about these boundary regions, so let's get on to building an API. So when we think about checkpoint and restart, the reason we think about checkpoint and restart is our machines aren't as reliable as we would like. If our machines were incredibly reliable, this would not be a topic for discussion today. We would focus instead only on saving your critical science data so that you can solve your science problems. But reality is that chances are if you run on an HPC system at large scale, sooner or later the machine is going to crash on you relatively far into your job. And if you haven't done something to save the data that represents the state up to that point, then you're going to have to start over again. And if you run big enough jobs or long-running enough jobs, or you get on a machine that is having a bad day, you may never actually get to the answer, right? And so people checkpoint. And so when I say checkpoint, in case you haven't heard that term before, it simply means taking the critical state of your application and putting it somewhere else outside of the system, usually in a file, so that were your application to crash or part of your application to crash, you could start back from some intermediate point rather than from the beginning. That's it. And so then restart is just the code that you wrote because you finally had a checkpoint that you needed to read, right? So that's it. Sometimes people will use checkpoint output also for analysis, right? Because it has all the critical state in it. That is a reasonable thing to do until you get to the point where your checkpoints are too expensive to write as frequently as you would like, right? Maybe it takes you half an hour to write your checkpoints. And maybe you'd really like to see the state of your simulation every 10 minutes. Well, you're going to have to do something else, right? Or otherwise you won't make good progress. And unfortunately, as we sort of alluded to earlier, I/O systems are sort of getting relatively slower, and so it is becoming more and more the case that people do something slightly different for analysis than they do for checkpoints. You tune your checkpoint based on some expectation of how frequently the system is going to crash, and there's papers about that. And then, seriously, there's lots of papers about that, multi-level schemes, all sorts of crazy stuff. And then you do something separate that is convenient for you for answering the questions you want to answer for your analysis. But the tools that we'll talk about today are good for both. Okay, so we're going to look at checkpoint. So we need enough to restart, right? That's pretty clear. So usually it's helpful to add some information in there that sanity checks. So say, for example, the size of the problem, right? That might be a good thing to capture. Maybe the input parameters, that might be a good thing to capture, particularly if it's going to be some time before you come back to this, just to make sure that you are starting what you thought you were starting. In our case, we're going to store this into a single file. We talked about this earlier. There are other choices there, but it's a good place to start. And because our application runs in this nice sort of iterative mode, it is very natural for us to have all of our processes stop at the end of an iteration and write their data out together. And so that is a naturally collective operation. And so we're going to get to take advantage of the fact that all those processes arrive at roughly the same time. And we're going to build ourselves a collective checkpointing library. So we're going to build an API for this. We're computer scientists, so we're going to over-design this thing because that's how we work. So we're going to have 5 functions. We're going to have an initialize and a finalize. We're going to have a checkpoint. We're going to have a restart function. And we're going to have an interrogation function that we can use to see whether this particular implementation can restart or not, because, again, we're CS people. And we can implement this for different backends. You're going to see 3 implementations. The first one is going to write to standard out. So can restart is going to return no. OK. But it gives us a nice way to sort of think about the problem. So a checkpoint routine is written with writing out to a file in mind. And so it takes a file name prefix, and that way we have a name to associate with things. It then takes a reference to the local matrix data, and then also the rows, the columns, the iteration number, and this MPI info parameter, which is a way to pass in performance tuning information. The way our checkpoint routine is going to work, our first implementation, like I said, is going to write the standard out. MPI standard doesn't really say anything about exactly how standard out is handled. And so if you've run on different systems, you've probably noticed that sometimes standard out gets pretty well munged between different processes. And so this implementation ships all the data back to rank 0 and then outputs the data in a nice sane order from rank 0. Not a very scalable algorithm. You wouldn't want to use this for 768,000 processes, but you're probably not running game of life and looking at the output on that many processes anyway. So it's a good example to start with. Okay, so we're gonna walk through the code. There are notes on these slides where we are in the code, but I'm going to show the code, so that's just sort of bonus material. So again, this is collective. The interface talks in terms of sort of the global array, and the output is going to be this single sort of logical view independent of the number of processes. So you could run this with 1,000 processes, and it might run slowly, but you would get the same single sort of view of the matrix that you would get from 2 processes or 10 or whatever. Okay, this is going to be C code. I'm sorry for those of you that don't talk C. I probably don't speak your language, but the concepts will be identical, and we can talk about quirky differences if needed. So the most important bits on this particular slide, one is, static is a scoping thing in C. So these are just functions that only are in this namespace of this file. I have prefixed all of my routines with mlife.io, MPI, game of life, IO. This is a type constructor, okay? You saw derived data types a few days ago, vectors and indexed and all that, okay? This is a type constructor that we wrote inside this library to build us a type that represents the block of rows local to a process, because we're going to use this 4, 5, 6 times, and by writing a function, then I could tell you that that's what it does, and then I can exploit it once and not have to show you the code over and over again, okay? And so what it's going to do is going to take a reference to the local matrix and a number of rows and columns and spit out a corresponding MPI type, okay? And it's actually pretty helpful to be able to do this sort of thing, or to do this sort of thing when you have a data structure like this you're going to use over and over. Okay. The other thing that's interesting here, I've got an MPI communicator down here that I'm going to use for all the communication inside of these functions, and I'll show you why that. I'll talk about that in a second. So here's where I'm duplicating whatever communicator got passed in, and saving it in that global I just showed you, and then at finalized time I'm going to free that. And so this is a good practice. What I'm doing here is taking an input communicator that someone has given to me for use in collective I/O for my checkpoint, and basically creating a copy of it. But what MPI does internally is creates what it thinks of as a new context, which is sort of like a new port in IP, for example. And the importance of that is that communication on this new duplicated communicator can't get somehow mixed up with communication on the old communicator. And so I've created an environment in which my library can communicate, and it is guaranteed that if I goof something up in my library, those messages won't get misreceived somewhere else, and vice versa. And so especially if you're creating a library and you're going to share it with someone else, this is a nice way of saving yourself some headaches by saying, okay, well, one thing I know is that my communication cannot get matched to someone else's sends receives with a different communicator. And so it's really just a safety mechanism. And as long as you're not creating hundreds or thousands of communicators, there's not a real performance overhead to this. So just knocking off an extra communicator so that you know your checkpoint communication isn't going to interfere with your application point-to-point communication is worth the effort. Okay, so that's an aside. But so here's our checkpoint routine. We're going to figure out how many processes we have. We're going to figure out which rank we are. And then we're going to use a couple of internal functions to figure out how many rows this process is responsible for, right? In case we've got it sort of a non-evenly divisible number of rows. And also what the starting offset in rows is for this process. So we're basically just figuring out which of those blocks is the block for this process. Here what we're going to do, again, this is our checkpoint routine. So if we're not rank 0, then we're sending our data to rank 0. And so we're going to create that type that I described and then commit it, because you have to commit types before you perform communication with them. Then we're going to MPI send our block of rows over to rank 0. And then we're going to free that type. And you guys have seen point-to-point communication, so I'm not going to go through all the little parameters here. That's not a good use of your time. But I'm happy to talk about this in greater detail during a break if you need a little refresher. One interesting thing here is MPI bottom. Usually this is a reference to a variable, something like that. So you may not have seen MPI bottom before. You can think of MPI bottom as sort of a situation where you have more or less encoded the address of the thing you want to send in the type. And so this, because we're passing this matrix reference into this type up here, that address is actually already encoded into the type. And so this is sort of saying, well, the address is in the type, so don't add anything to it, is a way to think about that. If we are rank 0, so else we're rank 0, we print out a little header that you saw on a previous slide. We print out our local data. And then for each process other than ourselves, we allocate some space to make sure we have enough space for that data. I was a little lazy there. Receive the data from the other process, print it out, and free that space up. And this is just so I didn't have to calculate the maximum amount of data I needed for any process. I was just lazy. And so that's it. So rank 0 prints everything for us. We have a little sleep down here in case you decide to run this for fun. It pauses long enough that you can see what's happening, because otherwise it's not a very interesting application to watch. And that's it. So let's talk about that function, the row block function, a little bit more. So recall we've initialized all these our boundaries to zeros, and we've got some shared data potentially, or these may have been initialized to zeros too, depending on which rank we are. But there's a block of data that is the important state that's not initialized to certain values that we want to store every time we do a checkpoint. And there's a block on each process. A nice way to think about this is that this is an array of contiguous values with a little skip of a couple of values and another array of contiguous values, because I happen to know that I allocated all this memory as one big chunk, okay? And so if I take advantage of the fact that I allocated this memory as one big chunk, I really know how it's laid out in memory. I can use an MPI type vector to describe that, almost. So the type vector, I say, oh, well, I've got 4 rows, and the length is columns, and my stride is columns plus 2. OK, no problem, and it's an integer, and I'm good to go, except that I'm not starting at the right location, right? Because I need to skip these values. And so the easiest way to deal with that in MPI data type constructors is to build a vector and ignore that problem for a second, and then to slap an h-index on the thing that bumps it to just the right location. And in fact, when we do that, we go ahead and work in the address of the starting element entirely. And that's how we end up using the bottom back in the top level in main. So I don't know if that totally made sense or not, but the main thing is we can capture some regularity with the vector, The fact that we need to do this bit of offsetting at the beginning is inconvenient because a vector type doesn't allow you to do that. We make up for it by using an h-index type to position the starting first byte at the location that we want. And since we're doing that anyway, we just roll the address of the vector in, the matrix in. So to see that in code, here's our MPI type vector. We use MPI address to get the address of that 1,1 element that we're interested in, and then we call MPI type indexed, and then we free up the vector type so that when ultimately we free the main type, that gets dereferenced too. Does that sort of make sense after me saying it 3 times different ways? Okay, cool. So this is our print function, not very interesting. We cannot restart, and so we cannot restart. So now we're going to talk about how we might re-implement that in terms of proper parallel I/O. So that wasn't parallel, right? We shipped everything back to rank 0. That is actually not a bad I/O strategy if you don't have a lot of I/O to do. Certainly makes things simple. It's sort of good until it's not. And that tends to be how people use that technique. Basically, they implement that when they first start writing their code as a grad student or something, and then a decade later when they are really running at large scale, all of a sudden they're having problems. They're like, oh yeah, there are these I/O routines that all send the data back to rank 0. And yeah, so anyway, but that's okay. I mean, you know, if you're not having trouble, then you're not having trouble, so that's fine. So if we want to get the benefit out of our parallel file system, though, really we do need to create independent data streams that are driving that parallel file system and taking advantage of multiple resources. You know, again, from this sort of logical perspective, you were all presented MPI as a programming model earlier in this series. And in the same way that the MPI model is a convenient way to think about communication and ranks and all that sort of stuff in parallel programming, it turns out that MPI also captures a lot of the sort of underlying concepts that are necessary in I/O. So, you know, collective operations and this ability to do optimizations because you know everyone's participating, that's absolutely important in parallel I/O. Being able to describe these sort of complex data layouts to the library and then have it execute data movement, again, you've already seen an example of us doing that for communication, also critical for I/O. This ability to separate messaging you know, and operations from one library from another so that we can sort of reason about where bugs might be, for example, another place where that infrastructure is really helpful. And finally, non-blocking operations are another thing that is supported in MPI, and you can imagine that having the ability to sort of say, you know, here's some I/O that I'd like to occur, now let me go back to computing and I'll come back and check on whether that completed or not later. That's a useful capability. And so all those things are there in MPI, and so many years ago the standard was enhanced as part of MPI-2 to include I/O routines, and those are the routines that we're going to use next. So just to sort of beat you over the head with this collective I/O concept, it is absolutely important. If you have a reasonably well synchronized code, this is a big win. The notion is that all the processes in a communicator are going to make a call into a collective I/O function. Some amount of communication between those processes is likely to occur. Doesn't have to. It depends on how you've sort of tweaked some settings, but often occurs. Then those processes in response to sort of an understanding of what might be a better organization are going to probably shuffle data back and forth prior to interacting with the storage system using one of a number of different two-phase approaches like Rob discussed. Now, it is also possible to turn off those things even though you've made a collective I/O call. And so it's not really appropriate to say that a collective I/O call is synchronizing. It's better to say that a collective I/O call is probably synchronizing because there's always sort of a chance that you can go in there and turn off those optimizations. And sometimes it's better from a performance portability perspective, for example, to write your code as collective I/O code and then turn off the collective optimizations when you find a platform on which they're not working very well. Okay. So we're going to use the collective I/O functions. We're going to just dive very sort of lightly into the MPI-IO routines. I'm not going to tell you about all the MPI-IO routines. I'm going to tell you about the MPI-IO routines you need to do this particular job. And these are some of the little bit more complicated ones anyway. And so if you understand how these couple of routines work, you're going to be able to sort of deduce how the other routines work without me walking you through every function. So in particular, the flavor of collective I/O functions we're going to use they look like this: MPI file write at all. The file part means that we're into an I/O routine. Write, we're writing to a file. The at means that we're going to tell it an offset into the file as part of the call. Okay. There's another set of functions that let you use a seek function. If you're used to POSIX or fseek and all that sort of stuff, you can separate the seek from the write. That's a silly thing to do. It's not thread safe. It's one more call. There's no reason to do that. So we're going to put the offset in as part of the call, and you'll see where that comes in. And the underscore all is just a reminder on the function call that this is a collective call, and so we had better make everybody call this or we'll have an illegal program. Okay? That's it. So that's how you decode that. There's a read at all. There's also a read at that's not an all. Okay? There's a lot of flavors. In fact, you could build a table, and that'd be a fun exercise, I guess. It should be obvious, but in case it's not, each process gets to pass in its own access information. So it gets to pass in its own buffer. It gets to pass in its own data type. It gets to pass in its own offset into the file. And so by tweaking those parameters on each process is going to say, well, this is the stuff that I have in memory, and this is the location that I would like this in the global file. Some other process has some other data in a different location in memory and wants to drop things into a different location in file, right? And in fact, something that oftentimes comes up, you can have a process that says, you know what, I'm going to make this call, but I have zero data to contribute to this, so that you can use a collective I/O function even though maybe you've got an irregular distribution of data, and it's more convenient to just have someone not participate really, not contribute to the call than it is to make a new communicator or something like that that doesn't have them in it. And that's a valid input. Okay, so the things that you're going to see here, you're going to see the same MPI data type being used to describe that block of memory, and then we're going to build a slightly more complicated one to capture the rows, the columns, and the iterations. You're going to see us use this MPI offset to locate our data in the file, and you're going to see a little bit of extra data on process 0, specifically that row, that column, and that iteration information. So when we decide we're going to build checkpoints, earlier we said, well, we need to have a canonical representation. We need to make sure we capture everything that's important, et cetera, et cetera. What does that mean? Well, now that we're actually writing to a file, it's worth having a diagram that spells out exactly where things are going to go in this file, right? And so because we're dealing with a file abstraction on the back end, we're going to have our rows as an integer, and then we're going to have our columns as an integer, and then we're going to have an iteration as an integer, and then we're going to follow that up with all of those rows of data from those individual processes in rank order, and that's going to be our checkpoint, okay? And just as in the standard I/O version, we're going to skip those border regions that are replicated on different processes, okay? And again, if I had been a little lazy, we certainly could have added those in here, but in many cases that redundant data adds up, and so we want to sort of show you a good example of working around that. Okay, no-go cells, global canonical order. All right. What we're going to do in this implementation in our checkpoint is orchestrate it such that all of the I/O for that entire diagram gets written out in a single collective call, okay? So we're not going to write the header first and then we'll write all the blocks. We said as a general principle it's good to try to get as much into a single call as possible, and so that's what we're going to do. It's actually not that much work, and so I think it'll be pretty obvious once you've seen it how you might do that for more complicated examples. On restart, we're going to do 2 steps. First, everyone's going to read the number of rows and columns from the file. okay? And you're going to see me do that with a collective read, which is totally overkill for this particular problem. But by doing that, I don't have to get into a whole additional set of functions and their semantics. And also, I don't have to do a broadcast and so forth. So it actually turns out to be simpler to show you that other approach of reading in one place and broadcasting would be totally fine. Assuming that the processes read that data in and things match up, they're going to use a second collective call to read their regions of data, okay? And it's just worth mentioning that because we're storing in this canonical format, it really doesn't matter how many processes wrote the data originally with respect to the restart. You can start with a different number. Okay, so this is our checkpoint function. Some things of interest. This A mode is an access mode. We're writing to the file. We're going to create the file. And this is a parameter that is a nice thing to pass in, but basically gets ignored, which says that, yeah, we're the only processes writing to this file right now, so don't worry about other applications conflicting with us. Doesn't really get used, but not specifying that might one day cause performance problems, so it's a good thing to do. In the same way that you get MPI communicators, MPI files are a way to reference files that have been opened under the MPI library once you've opened them, and so we'll have that reference. MPI offset, similarly, we're going to calculate our file offset, and that'll be where we store that. We're going to calculate our rows and row offset as we did before. We're going to use a eccentric C function to create a file name. Sorry, that's the sort of thing C programmers do, is use eccentric C functions to create file names. Then we're going to call MPI file open. MPI file open is a collective call. I don't know why they didn't put _all at the end, probably because there isn't an independent version, but it is a collective call. It's collective over the communicator that you pass in, and this is that communicator we duplicated from before, okay? Here's our file name, our access mode, that info parameter that we passed in that we could use to control two-phase and things like that, and we get back a file handle, and we should get success. Okay? If we're on rank 0, we're going to create a special type. So I built a second type constructor. We're going to create a special type that creates that little header in addition to the row block. Otherwise, everybody else is going to use that same type create row block that we used before. Okay? So you've seen that before. The second thing the processes are doing, rank 0 knows it's starting at offset 0 in the file. Everyone else is calculating a file offset, and they're leaving the space for the 3 integers plus leaving space for all the rows that go before them. That's it, right? So this is, the first thing is describing the data that's in memory, and the second thing is describing where that data is about to drop in the file, okay? Commit the types. MPI file write at all. We pass in our file handle. We pass in that offset that we're saying this is where we want our data in the file. And then this bottom one in type is the data that's in memory. Everyone makes the call. The call completes. The data is in the file. We close the file. Our checkpoint is written. Okay? And you know, again, sort of behind the scenes, what just happened was communication occurred between those processes. They decided on a strategy for breaking up this big file region into regions that aggregators are going to be responsible for. Data was shipped back and forth as appropriate into aligned regions to go to the file system. POSIX calls were called, and data was moved out to the storage system. And then once all that finished up, control was returned back to the application. And all that was done with a single call, so you know that. It's good to know that, but you don't have to really think about it on a daily basis. You don't have to write any code. Okay, so that's checkpoint. Pretty straightforward for a dense array like this. Restart is slightly more complicated. Access mode is read-only. And again, completeness. Size and rank. Calculate our rows. create a file name, open the file again, should get success. Now we're going to read into a buffer 3 integers, and we know from our format, because we made it up, that that ought to be a rows, a columns, and an iterations. Okay. We're going to do a reduction on the error code that everybody got back, basically just to verify that that everybody succeeded in reading the data. It's a little. I'm really just showing you a way to check input parameters, more or less. It is sometimes the case that certain processes can't read from a file system, and so this is a sort of a sanity check that your file system's working right too. From there, assuming that works right, we're going to do our type create row block that you've seen before. We're going to calculate our file offset the same way we did before, and now we don't need to read the row, column, and iteration because we've already got it in memory. And so we'll do file read at all. Again, it's a collective. We're passing in the location in the file we want to read from, and then a location, a type, a count, and a type for where we would like that data in memory, right? Basically like a receive. And then when the function completes, we've got the data in memory. Okay? And then we file close. All right, pretty straightforward. Any questions about these 2 bits? Probably maybe simpler than you thought it might be. I don't know. I've presented this slide a bunch of times, so I don't know anymore. I want to sort of iterate on that second type constructor just a little bit more, mostly in case you haven't done a lot of MPI data type construction. It's a sort of a thing that I'm particularly fond of talking about for reasons that aren't important. We're going to wrap a structure around the row block to add in those types, and I'll show you what I mean. So what we want is a structure that allows us to describe a rows, a columns, and an iteration that are stored in memory somewhere in variables, right? Maybe not right next to each other, right? We don't really know. Plus this block of rows that we do know is allocated, and we know we can describe with this vector plus index trick, right? So that's our goal, is to sort of describe that set of 4 sort of logical elements. Okay, so the way we do this, so this is our type create header row block. The first thing that you should know is that I'm going to be lazy, and I'm going to describe the block of rows using the same function I wrote before, because there's no reason to re-implement that, right? So the interesting thing is how I roll in the 3 integers. It's actually not that interesting if you've ever used MPI struct, but many people haven't. So we're going to get the address of our rows, our columns, and our iteration variables and stick them in this displacements array. And then we're going to put the MPI bottom in the 4th displacement array. And then we're going to say, okay, well, rows is an integer, columns is an integer, iterations is an integer. Oh, and this 4th type is one of these funny row block things. And then we're going to call some flavor of the struct creation function depending on what version of MPI you've got. This is the newer one, MPI type create struct. And so type create struct, why is that a 3? That's really interesting. That should be I'm almost certain that should be a 4. I feel like somebody added a parameter on me. Anyway, we'll look that up. That'll be extra credit. You guys can shame me for having a 3 when there should be a 4. The links, which are mostly 1s, all 1s. The displacements, which is this array here. The individual types, so 3 integers, and then this row block. And we get a new type back. And I have no idea why that's a 3. That really ought to be a 4. I don't write enough code anymore, but I'm pretty sure. So because that is how many things are in these arrays, which the answer is 4. Okay, so sorry about the bug, but that is how that ought to work. We're not going to. I'm not trying to tell you that you should go and build custom libraries using MPI-IO to checkpoint and restart. That is not what I'm trying to tell you. The 2 things I want to get across is one, that it's not that hard, really, to take. If you understand your in-memory data structures, honestly, you're 80% of the way done to building a reasonable checkpoint and restart facility. assuming you don't really need to share it with anybody, right? Because if you're sort of the only consumer of this internal data representation, then you can take your data structures and you can sort of you could sort of draw a diagram and go, this is how I'm going to serialize my data structures, cool. Work out the details of the MPI calls and make it happen. And honestly, that ought to be pretty fast, especially if you spend even just 10 minutes interacting with somebody that knows the rest of these layers pretty well. They're going to be able to steer you towards a path that's going to be pretty fast. You should go from nothing to reasonable fairly quickly. But what you're committing to is then building similar routines and linking them into any analysis code that you're going to use, right? And that is sometimes a high cost and sometimes not. So if you've got your own set of custom analysis tools and you're already building readers for it, there's really not much reason not to do this. However, if you are relying on, let's say, VTK, pair view visit, et cetera, and you want to save yourself some time, a lot of times it's faster to go in those libraries from a NetCDF or an HDF to a working analysis routine than it is to have to hack up a reader for your custom format. So, the thing I want you to get from this is, one, here's sort of a skeleton of how you might build a set of checkpoint restart routines or even analysis output routines if you need to do that. This is sort of just a starting point where you can say, okay, well, this is sort of the set of functions I might need. Here's some principles to follow, et cetera. And then if you do want to build an MPI-IO, great. But we're going to show in just a second a third example where we look at how we might do take the same API but do a different output format in one of these structured libraries. And in fact, the outcome there is that you can take an API like this and then change your mind about what output format you really want. And if you've put that layer in there, you can make that decision at relatively low cost. So that's going to be the last bit of MPI-IO for a little bit, and I've got like 0 minutes, but if we had a quick question that anybody wanted to ask right now, it would be a good time. Yeah.
So you've been doing the serialization yourself here, but I believe there are libraries for C++ for doing that automatically, but there's a bit of overhead incurred. I don't know if in practice you use those, or do you still just do it all by hand?
So the question was about serialization and the use of external libraries for serialization versus doing it by hand. We do a little bit of everything. It depends on the context. So we use XDR in some contexts. We use boost macro stuff in some contexts. We do things by hand like this. In part, it depends on how we're interfacing into the code. So for example, if the code is already doing a bunch of work where it's describing its data structures in MPI, you've probably got the code you need to do this serialization laying around somewhere, right? In which case, there's not necessarily a good reason to grab some third-party piece, right? On the other hand, if you know, for example, that you're going to need to take this checkpoint and use it somewhere else, right? Maybe it's a different platform. Maybe it's worth spending the time to serialize using one of these third-party libraries so that you've got a standard serialized output, and you don't have to worry about Indianness or something like that, right? So it's a good question, but it's sort of a case-by-case basis how you want to handle it. One more question, thanks.
You suggested the use of MPI data types for doing file I/O. That's sometimes suggested for communication, but usually suggested against because vendors haven't optimized because people don't use it, so vendors don't optimize it.
Right.
Is that better for file I/O?
So the question was about data types and particularly an observation that sometimes data types are really slow in the communication context, or at least we have anecdotes that certainly make that the case. And is that different in MPI or in I/O? So it is different in I/O. The reason that the situation is somewhat different in I/O is that this latency cost per operation is so high in the I/O context that first of all, you often don't see the overhead that you see in the communication context. I mean, there's still overhead there, because you still are taking a general purpose data type manipulation function and using it to do something that you could build a custom function to perform, right? But usually the other latencies in the system are such that you don't really notice it. And also, you can use the MPI data types to describe non-contiguity in file, and there's no other way to do that and send the data into MPI. And so in other words, if what you've got is a whole bunch of different regions that you want sort of interleaved in the file, the only way really to describe that in a single call is to use the data types. So if you're going to spend some time to not use the data types, spend that time on the memory side of things. You know, maybe you do some packing of your data structures into memory, right? But you're still going to end up using the data types on the file side. But I mean, I built a lot of the data type code, so I'm the wrong person to ask because I want it to be fast, right? But yeah, it is there. It's just not as big a deal. And I think I should probably stop at this point because now I've put us back behind. But thanks for asking questions and humoring me.